This is the last question of the practice SAC. The element boron has two naturally occurring isotopes, B10 and B11. The percentage abundance of the isotopes of boron can be determined with a mass spectrometer. The diagram shown the operation of a mass spectrometer. Okay, terrible. I don't think I have proofread this. You need to first of all state the names of stages R and S. Okay, because you already start with a gas, according to the diagram, there will not be any vaporization necessary. So I think Q must be ionization, which is when you bombard the sample with high energy electrons, and that causes B to turn into B plus, which should make R acceleration, which is when you, I don't know why it's flying up there, when you just supply it to an electric field, and that just speeds up the ion. So R is acceleration, followed by S. Now S is probably the most important stage in mass spectrometry, and that's deflection. So that's when the positively charged ions move towards the negative terminals of the magnetic field, but it will move a different degree. It will deflect differently. What am I talking about? Yes, it will deflect differently depending on how heavy it is. So S is deflection. Okay, so you need both of these for the first mark. I think it's a half a mark each. Deduce the number of protons, neutrons, and electron configuration of the main ion of 11B formed in stage Q. All right, so Q, as I just mentioned earlier, has to be ionization, and when ionization happens, the atom turns into a positively charged ion, so still in gas form. Now you don't have to write this equation. I'm just trying to show you what it happened in stage Q. So you have high energy electrons supplied. Okay, so basically you need to work out the number of protons, neutrons, and electron configuration of this ion. Now for 11B plus, the number of protons, now you had to check the periodic table. If you don't remember, for the number of protons of boron, which is also its atomic number, and it's 5, so the number of protons will still be 5 because you didn't lose any proton, you lost an electron. The number of neutrons, because this is proton 11, the number of neutrons will be 6, and the electron configuration, that's okay, electron configuration, you don't need to remember how many configuration, you need to remember how many electrons are in here and what electron configuration is. Because it has lost one electron here, it only has 4 electrons left. So electron configuration will be 1s2, 2s2. That's it. Moving on to the next part, in order to determine the percentage abundances of the isotopes of boron, samples of boron from different sources were collected. This data would then be used to calculate the relative atomic mass of boron. The first sample, sample A, was from brine in a volcanic crater lake in southeastern Australia. I did have some fun reading about this. I will just say that. And run through a mass spectrometer, the following result was obtained. You need to work out the relative atomic mass, what just happened, of boron based on this sample. Okay, this is very simple. We just need to work out the relative atomic mass using the two relative isotopic mass. So times 81.07 over 100 plus 11.009. Please show me some working out when you do the SAC. It will help me to give you any consequential marks, especially if your final answer is wrong. Not to say that I hope it will be wrong, but I'm just saying. What is that? Okay, so, whoa, you definitely saw that. Is that a sign that's going to die or something? Because I really don't want to record this again. I think last time I said that, it literally died right after I said it, so maybe I should stop saying things like that. 18.93 divided by 100. So I have 10.2, which is actually very different from what is reported on the periodic table. Oh, sorry, I was gonna write unit there. You shouldn't have any unit. Okay, what is it? 10.200. Yeah, 10.201. Actually, that's wrong. 10.201. Next part. Another sample B. A boron was taken from a metamorphic mineral in Antarctica. So the first sample, according to this question, was from Australia, and the second sample was from Antarctica. The boron in this sample still consisted of 10 and 11 boron isotopes with the same relative isotopic mass. Using this sample, the relative atomic mass of boron was estimated to be 10.8062. Compare the relative atomic masses of boron calculated using sample A and B above. Account for any difference. So obviously there is a big difference, is that the relative, so you need to make a comparison first, and the comparison in this case will be that the relative atomic mass of boron in sample A is smaller than in sample B. The relative atomic mass calculated, why does it keep getting darker? Calculated using sample A was lower than when using than sample B. So that's the first part. You just have to make a comparison. You need to make sure you answer everything that's asked, because a lot of the time people are so fixated on trying to explain that they forgot to answer the question, which is to actually make a comparison. Now you need to account for the difference here. Because the question tells you that the two samples contained the same types of isotopes with the same relative isotopic masses, the only thing left that may vary that account for this difference is that they just have different percentage abundances because they were taken from different sources, and that's all you really need to say. And even though it's a very simple thing, people actually don't realize that you can have different percentage abundances if you take samples of the element from different sources. So this difference was due to variation in the percentage abundance. This is so exciting, of the two isotopes in the two locations. So you have different two locations, you can have variation in the percentage abundances of the isotope. So one mark for making the comparison and one mark for pointing out that you can potentially have variations in percentage abundances. And that is it for this practice SAC.